Good morning, it's Mr. Miller and it's Thursday morning and several of you requested a clarification on the Mendelian Lab. So I will go ahead and go through that with you quickly in this video. Um, Several of you tried to turn it in late, so what we're going to do is we're going to go ahead and extend that deadline until Friday. So if any of you need to make corrections, clarifications, edits to your lab, go ahead and submit it on Friday before 10 o'clock. So before I actually go over the lab material, just wanted to point out to you that several of you are not watching the videos. The videos are there for your support, for your knowledge, for you to gain an understanding. And I know some of you are just using the PDF that I am also sending out. That PDF is good, but there are things that I say in the video that go beyond what can be put on that handout. So it would be in your best interest to make sure you are watching the videos. And yes, I can track them. I know how many views there are, and since there are over 180 of you in the 7 classes, I would say that several of you are falling way short on watching the videos. So as I said earlier, several of you emailed me in the afternoon on Wednesday or late Wednesday night, right before the lab was due, requesting clarification or saying you weren't sure what was being asked for in the lab. So in the lab, we were talking about Mendel's crosses, and we were using the coin data from the coin flips to show how the ratios and probabilities can be calculated. You did need to watch the video so you understood principles of dominance, the principle of segregation, and the principle of independent assortment, which will help you answer some of these questions. So when we're looking at the crosses, we are looking at the crosses created by the flipping of the coins. And the coins, of course, I hope you all realized were heterozygous since they had a capital A on one side and a lowercase a on the other. This matches Mendel's F1 cross, and that F1 cross is what we're trying to figure out what are the numbers and the probable ratios for. So when we use the Punnett square, we end up getting genotypic ratios of 1 to 2 to 1 and a phenotypic ratio of 3 to 1. Now, as a reminder, Mendel had his original parents, which were pure for tall and short. He then crossed them and getting all outcomes of heterozygous in the F1 generation. And then when he crosses the F1 generation, which are both heterozygous, we end up getting 3 dominant and 1 recessive, being 1 homozygous dominant, 2 heterozygous, and 1 homozygous recessive. The genotypic ratios being 1 to 2 to 1 and 3 to 1. Now, this is if everything is perfect, and this is only a mathematical probability. It is not what Mendel got, and I talked about in the video that Mendel may have fudged, adjusted his numbers a bit because the mathematical numbers and the lab numbers that he we're seeing were not exactly compatible. Now we know mathematically this is correct, but in nature is that always going to be the case? So you were asked to get a 10 toss count, you were asked to get a 100 toss count, and then I summarized the classroom data based on all of your inputs. Now unfortunately not everyone in the class put their data in, whether they chose not to do it or whether they simply didn't understand how to do it. Those are 2 different cases, and hopefully if you did not understand, you either reviewed with someone else or you sent me an email requesting clarification. When we look at the data, we are looking at the data for 10 tosses, and basically what you're looking at is how do these numbers compare with the ratios we see from Mendel and the probability from the Punnett square. And if that's the case, we should get a 1 to 2 to 1 ratio. Basically, the middle column, the heterozygous column, should be twice the size of the two other columns. So the homozygous dominant should be basically 1, the heterozygous should be 2, and the homozygous recessive should be 1, a 1 to 2 to 1 ratio. And again, with the 100 tosses, that basically comes out to a count of 25 for the homozygous dominant, 50 for the heterozygous, and 25 for the homozygous recessive. And you were basically supposed to take the numbers for your data and compare them to what the numbers would be from the actual Punnett square or from Mendel's data. Now, you were to compare the 10 toss, the 100 toss, and the full class toss size. Now, based on that information, how close did you come? How close were you to the actual ratios? Now, we do get unique situations because sometimes we do get more heads than tails. Sometimes we get more tails than heads. Sometimes we get double the heads. Sometimes we get double the tails. So if you look, we don't have pure numbers here. This 3 to 4 to 3 should be more like 2 to 6 to 2. So what we're looking at is a 10 toss count better? Is a 100 toss count better? Or is the class toss count better? Because what we're looking at is when you do more, when you have a larger population, you're going to be closer to the actual outcome because there are unique happenings. There are unique times where things don't come out exactly as we expect. When we flip coins, we would expect a head and then a tail and then a head and then a tail because it's a 50-50 chance. But sometimes do we get 4 heads in a row? Yeah. Sometimes do we get 7 tails in a row? Yeah. Those are unique situations though. And so when we look at an individual set of 10, that's not going to be as accurate as a larger population, say the full class size. And that's what you're being asked to answer in these questions. So in question 11, you're being asked to look for those outliers. Did you have or did you see any classmates who may have had a count that was not close to the 1 to 2 to 1 ratio? Did you have a count that may have been 7 homozygous dominant, 1 heterozygous, and 2 homozygous recessive? Because that would have been off from the actual expected results. And you were supposed to basically look for those outliers, those unique situations where maybe the counts don't match up to the expected outcomes. Then you were supposed to talk about, based on Mendel's results, did he or why may he have not gotten the numbers he expected? And was it okay maybe that he adjusted his data accordingly to fit the math that was expected? And then lastly, for question 13, you're looking at that law of segregation and independent assortment, and we're talking here about why is it that sometimes families do have 4 girls, not 2 boys and 2 girls when they have 4 children. Each independent organism, each independent offspring has the same probability as all the other offsprings. So while it may be true that you should have 50% boys and 50% girls because each offspring is independent, that's not always going to come out exactly the way we expect. So these are the things we were looking at, and if you need to go back and make adjustments on your lab and go ahead and turn that in by Friday, that's okay. But please, like I said, there are things in the video that I cannot put in the handout and vice versa. So it is worth putting both of them together for your knowledge base so that you are better suited to answer the review packets and the quizzes and eventual midterm that will be coming up. Lastly, I miss all of you and I miss being in the classroom with you and sharing our knowledge community, our learning community. But please stay safe, stay healthy, stay home, and stay happy. And please go ahead and continue working hard and learning as you go. Take care. Have a fabulous day.